Welcome to this particular lecture. In this lecture we will see electronic module for heating PT100 and operating as a hot wire anemometer to find the velocity of air. Now, what exactly anemometer is, what do we mean by anemometer, and what kind of electronic module you can design so as to understand the operation of that particular system. First let us understand the principle, and then I will give you an example of how you can design a quick sensor to understand the velocity of air if you do not have anemometer with you. Okay. So, first let us understand what is anemometry, and if you see the slide, anemometry is the measurement of velocity of gas or air. If you want to measure the velocity of air or gas, you can use the device called anemometer. And when you talk about thermal anemometry, it is the most common method used to measure the instantaneous fluid or air velocity, while its principle is that the heat transfer in the fluid dynamics to compute air speeds and uses electrical circuits. So, when there is a heat transfer in the fluid dynamics or in the let us say I have a cylinder in which I am inserting a air and the air comes out from the cylinder. Okay. I want to know what is the velocity of this air that goes inside the cylinder or that passes through this particular cylinder. What I can use is the anemometer. Now, the another way is that if I am passing instead of air a fluid, then also I can use the anemometer. And in one of the lectures you will see how can you design the fluid dynamics, or how can you do the simulation for designing such kind of fluid dynamic system using a software called Comsol Multiphysics. Comsol Multiphysics. We will see detail about simulation software in one of the lectures. For now, let us understand that how can you design a system that can measure the velocity of air in this particular cylinder, and in particular if you have, so that is a kind of sensor, right, that is a kind of sensor or a transducer. And if I want to change the value the output of the sensor to a readable format, I need to work on the signal conditioning circuit, and that is a part of this particular module. So, let us understand the principle of anemometer, and then we will go to the next slide. I will play this particular video.
Hello and welcome to the Titus Timeout podcast. I'm Jenny Abney-Civy, and today I'm going to answer the question, what is a hot wire anemometer? So I was thinking about the hot wire anemometer the other day, because that's what you do when you work in HVAC, or maybe it's just me. But anyway, I thought I'd make it this week's podcast. Hot wire anemometers used to be an option you can get on our VAV boxes. We aren't asked for them much anymore, but you will still see them in lab equipment for measuring airflow. So first of all, what is an anemometer? An anemometer is a device used to measure airflow. So those spinning cups you see measuring wind are a type of anemometer. So when the wind blows, it spins. You get the point. So are pitot tubes that you see in VAV boxes, as well as crossflow sensors in the Titus VAV box. So a hot wire anemometer is pretty much what it sounds like. It's a very fine wire that is heated and put in airflow. Air flowing past the wire cools the wire down. Since the electrical resistance of the wire changes with temperature, you can use this change in resistance caused by the temperature drop to calculate the airflow across the wire. So a hot wire anemometer looks something like this. So it's usually on the end of a long probe or stick so that you can put in the airstream, and then there'll be a little piece to protect the wire on the outside, and then you'll see the wire on the inside, and you'll put it so that the air flows through the opening and over the wire. It's a pretty simple device, but we use it every day to measure the airflow in our lab. So that's all a hot wire anemometer is.
Okay. So, you have seen this particular video, right, and what you understand is that what is the principle of the anemometer. Okay. Now, another point is if I want to use anemometer, which kind of anemometer, because you see if you have flow meters, you have mechanical type, you have electrical type, right. And then you if you further understand, then there are liquid flow meters, then there are air flow meters, and there are gas flow meters. So, if I talk about air flow meters in particular, because we are focusing on the measuring the velocity of air, then we have a volume. So, in the last slide what I have shown you is the principle behind anemometer, but if I want to measure the flow of liquid, then also I can use the flow meters, but we are focusing on understanding the hot wire anemometers in particular, and that is why we are talking about airflow meters. So, like I said, flow meters can be divided into two type, mechanical and electrical, and then further we have liquid type of flow meters, we have liquid flow meters, we have air flow meters, we have gas flow meter, and in further air flow meters we have pressure flow meters, we have volume flow meters, and we have velocity flow meters, or called anemometers. Now, further you want to understand what are the kind of anemometers, then we have cup anemometers, windmill anemometers, pulse width modulation based anemometers, then we have hot wire anemometers, and then finally we have a laser Doppler anemometers, or we can also have a sonic anemometer, or we have ping pong ball anemometers. If you further divide hot anemometers or hot wire anemometers, then we have constant current anemometers, while we also have a constant temperature anemometers, right. So, this particular diagram is extremely important to understand the different type of anemometers, and then we will see the working principle. As flow rate varies, the conventional heat transfer coefficient varies, and that causes the change in the heat transfer from the filament. So, what are the objectives? Measure the velocity of air irrespective of temperature change. Second one is device should compensate for the temperature of the air, and third one is the fast response, right, because we need to see the what is the change. And when we are talking about thermal anemometry, we have few assumptions and we should know when we can use it. First is that the assumption number 1 is that flow is incompressible, wire second assumption is wire is nominal to the flow, and third one is effect due to natural convection, radiation and conductions are neglected. These three assumptions are very important when we talk about thermal anemometry, where when we talk about when to use it, the device is to be used only when there is a clean operating condition due to their delicate nature, right. So, these are the some of the assumptions and the point. So, construction of basic model of for anemometry is with Wheatstone bridge. We will discuss about this particular design in detail in the experimental class, where the TA will teach you how to design the electronic module or signal conditioning circuit for anemometer. Now, just to give you an example, let me just show it to you how can you design an anemometer or a flow sensor if you want to understand the flow of the air in a cylinder, and assuming that is a hot air, okay, or just air, does not matter, hot air or cold air does not matter. So, let me just draw a schematic, so I can explain you what I mean. Suppose I have a cylinder and I want to design a sensor that can measure the flow of air passing through this particular cylinder, right, and the velocity of this air. Okay. I want to measure the velocity of the air through this cylinder. Okay. So, what can I do? The first and the easiest way is you can have heaters or a sensor with a heater, right. Here this is a contact pad and then this is a heater, and if I place the heater inside this particular cylinder, so let me just draw so it becomes easier, and I take up contact such that I have the contact on both the sides and the contact pads comes on the both the sides. So, here I can measure the temperature of the heater. Okay. So, now I have a heater in the center and these are the contact pads this one are contact pairs to the heater, and I am taking a contact out of the cylinder to measure the temperature of the heater. Now, you know that heater is nothing but a resistor, and we talk about resistor, resistor is nothing but depends on resistivity, length and area. If I increase the length, my resistance would increase. If I decrease the area, my resistance would increase. Resistivity depends on the metal that we choose, right. So, for a particular temperature, let us say at room temperature, I would have a base resistance of the heater to be 100 ohms, and as I heat or I just keep at room temperature, it is 100 ohm, right. Now, if I heat this heater, if I heat the heater to let us say 50 degree centigrade, I will have a particular resistance, right, delta R change to the initial value RBT, correct. Now, when I flow the air, what will happen? Due to the flow of air, this temperature would decrease, right. If my air is cooler, my temperature would decrease. That decrease in temperature will be corresponding to the decrease or increase in the resistance, right. The decrease in temperature will correspond to the change in the resistance of the heater, because finally a heater is nothing but a resistor, right. Either you draw the resistors in this particular format, or you have a rectangular format, right, or you have a meander shape, sorry, just right, meander shape, rectangular coil or spiral coil. All the three things what we are doing by using the spiral coil, what we are doing. So, actually it goes like this, right, and you have two contacts, right. It is not sorting, this is not correct, quite a little bit stable hand to get it done. So, you have a contact like this, right. Similar thing goes here, you require a contact pair coming out of this, right, without touching, and then you have here two contacts, right. Same thing goes for here, you have one contact here, you have second contact here. In all the cases, if you have seen, what we have done is by increasing the number of turns, we are trying to increase the length of the heater, right. So, if you want to perform the simulation to understand how the performance of these three heaters would be there, you need to work on Comsol Multiphysics, which is the next particular next lecture in which we will teach you this one, and that is related to lot of applications. So, the example that I was giving it to you here is that if I have a sensor or a heater at 50 degree centigrade, and if I flow air in the cylinder, what will happen? There will be change in temperature, temperature will reduce, and correspondingly I can measure the resistance. So, the change in resistance would correspond to the temperature change. Thus, this heater can also work as a sensor to understand the velocity of your air, right. Very easy to redesign the sensors if you understand the basic concept, right. Well, you know that when there is a flow of air, the temperature would change, and if I have a heater, then my heater will tell what is the velocity of the air. So, can I correlate that? That is the easiest way of doing it. If I want to fabricate a heater, I have taught you in my earlier classes how to fabricate a heater. You just quickly see, let us see how to fabricate a heater in the on the screen. So, if I want to fabricate the heater that I can use to understand the velocity of the air, it is very easy. What we will do, we will have, let us say if you do not have silicon wafer in your college or university, you can take glass. Okay. Now, what is the difference between silicon wafer as a substrate and glass? In silicon wafer, I cannot directly deposit metal, I have to grow silicon dioxide, right. I generally grow silicon dioxide. You have seen earlier lectures in which we were using silicon dioxide, or we are growing silicon dioxide on silicon wafer, and this silicon dioxide would act as an insulating material, right. What is glass? Glass is nothing but silicon dioxide, So, instead of silicon, if you do not have silicon, we can use silicon dioxide. There are advantages and disadvantages of using glass and silicon at some point, which falls more in the micro machining part, but right now let us focus on how to design a heater that you can use inside this particular cylinder to measure the change in the temperature, and that change in temperature will correspond to, these are the correspond to the velocity of air. These are the contact pads, this is COANTACT contact pads, and the material that we will be using is chrome gold, or let us use platinum, or you can use nichrome, that is easier, nichrome, right, and this one is my glass. I want to fabricate this particular heater. So, what I am doing is, first I take glass as a substrate, and on this glass I will sputter nichrome. What I will do? I will sputter nichrome, alright. Now, after sputtering nichrome, I will perform photolithography. So, first step is we will spin coat photoresist, we will spin coat positive photoresist. Next step is we will load the mask, right, but before loading the mask, what we have to do? We have to perform soft bake, right. So, after spin coating positive photoresist, here what we will perform? We perform soft bake at 90 degree centigrade for 1 minute on hot plate. After this, this is what is our nichrome, this is my positive photoresist, I have performed soft baking. Then I load the mask. What kind of mask I can load? I load bright field mask, I load a bright field mask, So, if I have a positive photoresist and if I have a bright field mask, then what will happen? The area which is not exposed by UV light, will be stronger. By this point, by this time, you should know this. Okay, this is what we are doing, UV exposure, right. So, if I perform this, this is my glass, right. The next step would be I will dip this wafer in photoresist developer. If I dip this wafer in photoresist developer, what will I have? I will have my photoresist protected in this sections, since this positive photoresist was not exposed because of the bright field mask, right. What is the next step? After this I will have hard bake at 120 degree centigrade for 1 minute on hot plate. If I perform hard baking, and then the next step would be to dip this wafer in nichrome etchant. If I dip this wafer in nichrome etchant, what will happen? I will have nichrome only saved where the photoresist is there, right. I will have nichrome only in the area where photoresist is there, remaining area nichrome will get etched. Easy. Now, next step is I dip this wafer, this particular wafer in acetone. If I dip this wafer in acetone, what will happen? It will strip off the photoresist. It will strip off my photoresist. If it strip off my photoresist, what will I have? I will have nichrome patterned in form of a heater, which is what is shown in this particular schematic. You got it? This is how we can fabricate a heater, and we can use a heater to understand or measure the velocity of air. Now, in the experimental class, let us see how can you use the signal conditioning circuit for using the hot wire anemometer, and then if you have any questions, feel free to ask, and we will be very happy to answer your questions through the NPTEL forum. All right. Till then, you take care. I will see you in the next class. Bye.